There was actually, and there will be a poster by my student Lena on this. We also work with quantum processing nodes based on single rare earth ions. I will talk about it a bit in this talk. And then we also work on, we like to combine different kind of systems together. So we work on quantum frequency conversion to make this very different system talk together. So today I'll speak mostly about the rare earth memories and the single ions in the solid state. So this research is in the context of quantum networks, where basically what we want to do is to be able to distribute entanglement between different kind of systems, between material quantum nodes that can be used to process and to store quantum information. And we want to distribute entanglement between many of these nodes via using photons, for example, traveling in optical fibers. And the reason why we want to do that, there are several applications that we can do, ranging from secure communication to distributed quantum computing or blind cloud quantum computing or distributed sensors. And if we want to make such a network to work, the quantum nodes need to have different requirements. The first thing is that we need to have this interface. We heard a lot about this interface this morning between the material node and photons. So we use photons to communicate. So we want really to have this interface between the two. Of course, these photons they will travel perhaps in optical fibers to go to long distance. So the photon should be at telecommunication wavelength. The memory doesn't need to be, as we will see, but the photon needs to be at telecommunication wavelength to travel in fibers. Then, of course, we want to have long-lived storage. So the qubits that are stored in the material node should live for a very long time in principle. And we also ideally want to have not only one qubit, but many qubits. So we would like to have a sort of register of many qubits that are stored into our material node. And last but not least, ideally, we'd like to be able to do some sort of gates locally between the qubits within one node to have some sort of quantum processing node that we can then network in distributed fashion. So there was many approaches that has many platforms that have been proposed to do such nodes. We heard a few of these platforms this morning based on laser-cooled atoms. There are also single atoms, single ions, for example. I will talk about rare earth doped solids. And there are also diamond, color centers in diamond, we will hear about later also. And finally, single rare earth ions, which is a little bit of a new approach that has come up in the last few years. So again, today I'll speak mostly about rare earth in ensembles and single rare earth ions in the second parts of the talk. So first, I will explain you what is a bit on the rare earth platform. What is it about, and how we can build nodes with this. Then we will look a bit into how we can create integrated quantum memories, waveguide-based quantum memories in this rare earth doped solids platform. And finally, we will look into how we can make quantum processing nodes with single rare earth ions. Okay, so let's dig into a bit of the rare earth. So the rare earth are these lanthanide, which are all of these elements in the elements table, and they are a very nice system for this kind of applications because they provide a large number of atoms with optical transition and with spin transitions, and they are basically they are impurities doped in a solid, so you don't need anything to trap them. You don't need laser light to trap them. They are sort of naturally trapped in the solid. And they have actually very good coherence properties. If you cool them down to around 4 Kelvin in a cryostat, they have extremely good coherence properties. So it's probably as close as you can get from atomic physics, but in the solid state. There are optical coherence with hundreds of microsecond coherence time, and spin coherence that can reach several seconds or even minutes of coherence time. So we are in solid, right? So there is inhomogeneous broadening in the solid. So each ion sees slightly different crystal environment. So they will resonate at different frequencies. So normally this is a bad thing. In our case, it will result to be a good thing because it will enable us to do some multiplexing, both in the spectral degree of freedom and also in the temporal degree of freedom. So we will use this inhomogeneous broadening as a resource for doing multiplexing. So we are in a solid state, so this lends us naturally into a way to make integrated devices. We'll talk about this later. And finally, the last thing is that nice, interesting thing about these ions is that they have a permanent dipole moment, which is different in the ground and excited states. And so this allows the different ions to have dipolar interaction between them. And we can then use this interaction, hopefully, to perform quantum gates within the ions. Okay, so let's now see what our node look like. So we are basically separating the entanglement creation and the entanglement storage. So our node is that we have a source of quantum light, which emits pairs of photons, and one photon is then resonant with our quantum memory, and the other photon is at telecom wavelength. And this allows us to have, in the end, entanglement between the quantum memory and the telecom wavelength, even though the quantum memory doesn't work at telecom wavelength. But what is important is that we have the photon working at telecom wavelength. So as a quantum memory, we use a technique that we called atomic frequency comb. So the idea is that we have a crystal, doped in our case with praseodymium ions, and we will create in that crystal, in the inhomogeneous broadening of this crystal, a structure with various periodic peaks, absorbing peaks, which have a periodic structure. And then we will come with a photon and absorb the photon into this structure. And this will basically generate collective excitation. We heard about this morning as well. So you have one atom excited, but you don't know which one. The excitation is distributed along many of the atom. And then this excitation will dephase because you have this inhomogeneous broadening. But after some time, because we have this periodic structure, there will be a rephasing. And when the rephasing happens, the photon will be re-emitted now in the forward direction. So this is a nice system. It's also nice because it's inherently temporally multiplexed, in the sense that if we now come with a train of single photons in the output, a train of single photon will also go out at different time. But so far, this is what we call a fixed storage time memory. So the photon is mapped onto the crystal, and then it's re-emitted, but after a fixed storage time, which is prepared beforehand on the memory. So if we now want to have the ability to read out on demand, on the push of a button, what we can do is then use optical control pulses that send the photon down now to a spin state, and then we go from a collective optical excitation to a collective spin excitation. And this now will allow us basically to have, first of all, on-demand readout, because now you can read out this spin excitation on demand with another laser pulse, and also to have access to the long coherence time that you have in the spin state of these memories, which again can reach seconds or minutes. So this was for the memory. Now for the source, we need to have an entanglement source which is compatible with our quantum memory, and which has these two very different wavelengths, these photons at resonant with the praseodymium memory, which in our case is at 606 nanometer, and telecom wavelength. And for this, we use basically a parametric, cavity-enhanced parametric down conversion system, which allows us to have non-degenerate pairs with a bandwidth of 1 or 2 megahertz that is then compatible with our quantum memory. Okay, so with this, in the recent years, we've been working a lot with crystals in the bulk, let's say, and so we progressed quite a bit in that aspect. We, for example, generate entanglement between the memory and photon at telecom wavelength, and we used that to demonstrate that you can distribute now this light matter entanglement over a fiber network. We demonstrated entanglements between two spatially separated crystals in two spatially different cryostats. We created arrays of quantum memory in the same crystal, up to 10 different quantum memories in the same crystals. And finally, we progressed also towards high efficiency quantum memory with efficiency up to 62% demonstrated in that setup. But today, what I will talk about mostly is how we can now do integrated version of this setup using a waveguide kind of memory. So why we would like to do that? So this was mentioned a bit this morning. There are several reasons. One of them is about experimental sort of scalability. If you have this, you could in principle imprint many waveguides in one crystal, in one chip, and really have a massively multiplexed memory. Then you could also interface, for example, the quantum memory with other kind of circuits, or photonic circuits, where you could combine, for example, I don't know, interferometers or other type of elements together in the photonic circuits, and you can put quantum memories now into these photonic circuits. And then you can also ideally fiber coupled everything and have a much more stable quantum memory to operate. Then there is the advantage also of mechanical stability. For example, if you want to do to put an interferometer, two memories inside an interferometer, if it's on chip directly on the crystal, it's much more stable in terms of the phase. And finally, because you are confining the lights, there is this enhancement of light matter interaction that could be also useful in some instance. So there have been many different ways of doing this kind of integrated quantum type of memories. One possibility is basically to create waveguides, or let's say to create a memory in a material which is good for making waveguides. And this is, for example, lithium niobate, and you dope lithium niobate with rare earth ions, and you can make waveguides easily out of this. So this is very good for making waveguides. On the other hand, the coherence properties in lithium niobate, for example, are not extremely good. So there are some limitations in that also in that approach. The other approach is then to make directly waveguides on the material that you use for your quantum memory. And this has been pioneered by the group of André Pharaon in Caltech, where they really make waveguides using focused ion beam directly in the crystal used for the quantum memory. And this they have used, actually they have achieved quite nice results out of this. And finally, another approach is a hybrid approach, is to basically use a nanophotonic circuit, for example, in silicon, and then to basically place this circuit on top of a crystal that you use for quantum memory, and using evanescent coupling to couple the two things. So in our case, we use a different technique. So we also burn waveguides on quantum memory crystals. So these are good crystals for quantum memory, our praseodymium doped crystals, but we use a femtosecond laser writing out of it. So this is a collaboration with our colleague in Milan, Roberto Roselami and Giacomo Corielli. And what they do to fabricate this crystal is that they shine a femtosecond laser on the crystal, and this will basically change locally the index of refraction of the crystal. And in the end, it will end up guiding light into this structure. So it's a very nice way, very nice technique, because first of all, it's direct. It's cost effective, and it's a fast way to make waveguides. And then a very nice approach, also a very nice point, is that it has this 3D. It's actually one of the only approaches that can do that. This 3D fabrication capability. You can make waveguides not only at the surface, but also at different depth of your crystal. So ideally, you could have really massive multiplexing on a crystal, and then it can be used on a wide range of materials. Usually it's used in glass, and we have actually, for the first time, shown that this could be done also in this kind of crystal that we use. So we use so-called type 1 crystal, which means that basically the light is guided exactly where you have the burn with a femtosecond laser writing. And this has the advantage that this makes very small waveguides, just a couple of micron, and then this is now compatible with optical fibers. You can glue optical fibers to it, as we will show in a minute. So we did some experiments out of this. So first experiment that we can do is basically use our photon pursors, detect a telecom photon, which will then project the other photon onto a single photon at 606, and then store this photon into a waveguide. And this now, basically we can show that we can store a single photon in the waveguide for a couple of microseconds in that case, which is not extremely long, but still for this kind of integrated waveguide in solids, this was, at least at the time, much longer than what had been demonstrated before. So this is done now with one frequency mode. One advantage of these rare earth waveguides, as I mentioned in the beginning, is that they have also this inhomogeneous broadening. So you could, in principle, also store not only one mode, but many different frequency modes, burn many different memories at different frequency. So what you see here in red is actually the spectrum of our photon pursor. So you have these many frequency modes. And here in yellow is what is the spectrum after the quantum memory. So in that case, we burn only one memory, one AFC at one specific frequency. But we can also burn AFCs at different frequency and then store all the frequency modes directly into this crystal. So in that case, we had up to 15 frequency mode combined with 9 temporal modes, which made a total of 130 modes. Okay, and the last thing that we can do with this is that we can do a fiber integrated memory. So now the idea is to glue basically fibers to attach to the crystal. And so then all the light that comes to prepare the memory and to control the memory comes down all with this fiber. We have nothing coming from free space. And then we can actually see that we can do the same experiment as before, and we can see that we have now longer storage time, which is given by the enhanced stability because of the fiber pigtailing. And we also have been able to store entanglements in that case to demonstrate light matter entanglements in that case. Okay, so now in the last minutes, I want just to tell you about a different approach. Up to now, we were using a lot of atoms in our crystals. Now, basically, we would like to use to control a single atom, a single ion in that crystal. And the reason is that ensemble-based are very good for multiplexing. On the other hand, it has very limited quantum processing capabilities. But now, if we are able to detect a single ion and to control a single ion, you can have basically a long-lived spin-photon interface, possibly also at telecom wavelength. And then you had these permanent dipole moments that I showed you, that I told you about at the beginning, where basically you can have now quantum gates between two ions if they are close enough. There are dipolar interaction between two ions if they are close enough, a distance of a few nanometer or so. And also these rare earth ions, actually the nice point is that their coherence is actually quite well preserved when you put them into nanostructure. On the other hand, now to detect a single ion is not easy because you have very weak optical transition. And so what you need to do is to put now these ions into an optical cavity to have Purcell enhance the emission and to really be able to detect a single ion. So the idea, then the long-term idea would be to have basically some ions in some volume that can make gates between each other. Then you have a communication ion, which is connected to a cavity and which can create light matter entanglements, spin photon entanglements, and can connect now to another node that you can use to make sort of distributed quantum processing. And if you want to do that, then you need basically to be able to control individual ions at nanometer distance, and to read them out selectively, let's say. And also you want the ion to be close to each other, but still you want to control them, to address them separately. So let me skip that. There were also actually other different techniques that have been used. The technique that we use is to use nanoparticles and in open fiber microcavity. So why do you want to use nanoparticles? So imagine that what you want to have actually is to be able, again, so you have these different ions in your volume which have different frequency, and you want to be able to distinguish them, to read out, to address them selectively and to read them out selectively. So basically, if the volume is very big, you need them to put them sufficiently far apart so there are not too many ions and you can still read them out selectively. So now, basically, if you want to increase the interaction, so if they're far away, there is no interaction. If you want to increase the interaction, you will basically put more atoms, you will increase the doping concentration, but then you will lose this spectral distinguishability in the sense that now you are not able to address a single ion in that case. So how to solve this problem? The idea is that now that you can basically just reduce the volume and just have a very small volume where now you have a few tens of ions, a few hundreds of ions, and then you'll be able again to distinguish them separately and to address them in frequency. So the nanoparticles actually allow you to have high density and to give you strong interactions together with spectral distinguishability. So the volume that we use is actually about 100 times smaller than other approaches. And so in that case, we hope that this will be also good for doing this kind of interactions. So this is now our system. So we have nanoparticles that we put onto a mirror. And then we come with a fiber cavity on the together, which is put on a nano translation stage. Everything is basically fiber. We excite from the fiber, we detect from the fiber. And we have a cavity with a finesse of around 20,000 in our cryostats. And so this ideally should give a per cell enhancement of about 100. And this is what we could measure per cell enhancement with close to 100 value, and then we basically try to detect single ions in that structure. So we basically scan the fluorescence as a function of frequency, and then you see this. When you go a little bit away from the resonance, you start to have this isolated peak. We can zoom on the peak, so this is really a nice peak. Then you can park your laser there. You look at the fluorescence as a function of laser power, and you see that there is a saturation. So you have isolated spectral structure. You have a saturation of the fluorescence, so this looks like it is a single ion. But then, of course, the full proof is to do anti-bunching measurement, and then using this anti-bunching measurement, we could show that we can really detect a single ion out of this. Okay, so let me summarize now. So I showed you that using this rare earth doped solids, we can make quantum network node integrated, and also that showed you a new platform, let's say, for doing quantum processing using these nanoparticles, doped nanoparticles. And the last next thing to do, of course, is we want to increase the performances of all these nodes. We want to go further on the integrated memory arrays, for example, doing spin wave storage, which I haven't shown, and memory-enhanced photonic circuits. And finally, also generating indistinguishable photons from nanoparticles, and also ideally doing photon-photon gates and being able to push now the quantum processing aspects in this. And so, yeah, let me thank also my group and the sponsors, and thank you for your attention.
Thanks a lot, Hugues. Maybe we have time for one question. Then.
Thanks for the talk. Regarding the fiber cavity with nanoparticle, the quality factor that you mentioned, is it with the nanoparticle inside? Because in the end, the empty nanoparticle itself is a scatterer that should cause losses. So how does the finesse or Q factor change when you put the nanoparticle in the center of the mode?
Yeah, absolutely. So actually, it's true that it is a scatterer, and this is actually what we use to detect that the particle is there. We look at the transmission of the cavity, and when we find a nanoparticle, the transmission decreases a bit. So to give you a number, the finesse goes maybe from 30,000 to 20,000 or so when you put the particle in. So this depends, of course, of the diameter of the particle. It's a diameter to the power 4 or something like this. So it depends on the diameter of the particle, but we find particles which are small enough to be detected, small enough to not induce too much loss, but big enough to be detected, basically.
So maybe in the interest of time, we can move other questions to the coffee break. But thanks again, Hugues. And our next speaker is Hanna Jeannic. She'll be talking about quantum light generation and collection via solid-state emitters on optical nanofibers.
Yeah, thanks. It's like I'm tiny, so I hope the mic is like. Okay, so thank you very much first, Taco, for inviting me here. It's a great conference. I'm very happy to be here. So today we're going to keep on talking about solid states and nanofibers. So I'm very happy we had introduction talks before. And about quantum light. So obviously the first type of quantum light you might think of is like single photon, a single particle of light. And as we've heard today, what you would like to do is something deterministic, where basically you would push a button and it would generate single photon or any quantum states that will make you very happy. And there is a bunch of sources. We've heard of atoms today, there is ions, and there is all this solid state system, so defects in solid, for example, but quantum dots as well. And basically in all those systems, what you have is can be approximated in a two-level system, and you send a bunch of energy, here a big green laser, and you hope that in a deterministic fashion you can get a single photon out. Me, I'm in love with solid-state sources. Why? Because they are pretty bright compared to atoms or ion. As we've heard, you don't need to trap them. They are easier. Like there was Hugues' talk just before, so you can see that they might be easier to integrate to nanophotonic system. I'm putting like marks though. But why not solid-state sources, and what you can love atoms too. They have huge decoherence mechanism, like due to phonons, due to charges, and you typically need to cool them down to get a good single photon in general. Okay, so not saying that solid states are better than atom. I wouldn't go there. Okay, so once you have chosen your favorite quantum emitter, you might want to collect all the photons, right, to be able to have really this push button system. And it's a problem on how we can collect 100% of the output of your atom. We've heard today a bit about cavity systems. So you put two mirrors, and Hugues also was showing fiber cavity. In order to improve the excitation, to make sure you excite your atom, but also to make sure that your photons get emitted in the correct mode. For me, and for many other people at this conference, we've chosen another approach. We use waveguides, basically with either an emitter inside of the waveguide, or you will see for us close to the surface. And in this way, you can also try to collect your photons. So the nanophotonic waveguides we're using are nanofibers again. So basically it's like fibers with hundreds of nanometers diameter, and you have this evanescent wave that is guided. So the field is guided in the evanescent fashion around the fiber. And well, as you've seen in some nice talks today, what you can have is like emitters around the nanofiber interacting with the field. And in this way, for example, if you have emitters around the nanofiber, your single photon can get coupled into the fiber. So I think no one showed how to fabricate nanofiber. I thought Arno would have already said it, but so the way we fabricate nanofibers typically in the lab is we use conventional fibers that you can have at home, and we use a heat and pull technique. Basically, use a flame and you just pull your fiber. No, it's a bit more complex, but you just pull your fibers. But like you would do for a chewing gum, it gets thinner and thinner and thinner, and if you calculate correctly and you do things well and slowly, you can get to actually way below 500 nanometers, like 200 nanometers fiber, for example. And so then the advantage of solid states is we don't have to trap our atoms around. We can come with nanocrystals, as also Hugues was showing. We have them in solution, and we can just come with a droplet of solution and gently touch your fiber, and you can deposit single nanocrystal containing your emitters in it. So this is a ATM picture of a nanofiber with a single nanocrystal. That you can see. So you can see it's 250 nanometers of fiber, and the emitter is like 60 nanometers, pretty small. The crystal. The emitter is even smaller. And once you have that, so you have your photons that should get coupled into your fiber, and you can use second-order correlation measurements to check that indeed it's only one photon, not two. So the solid-state emitter we've been using are nanodiamonds, actually. So you might have seen that sometimes diamond is not transparent. It can be pink, or it can have other colors. And this is due to impurities. It's not perfect carbon. You can have erbium, you can have nitrogen in your diamond lattice, and that creates colors. So we call them color centers. But if you have only one impurity, actually it behaves like an atom. So it's like an artificial atom. And so what we have is nanodiamond with germanium or silicium centers in it, silicon centers, sorry. And so what we can do is deposit our diamond on top of our nanofiber. So this is a picture from an iPhone. You can see a little shiny scatterer on top of the fiber. And you can indeed check that it has single photon emission in the fiber. So all this is at room temperature. Let's not talk about undistinguishability. But so typically, when you use a conventional nanofiber, so for us with the solid state, we can be very close to the surface, so we get a bit more field than people in atom can have. But still, it's very limited. Like you can only couple if you do everything well and your dipole of your emitter is perfectly in the good direction. You can get up to 25–30% of your light inside of your fiber. So not bad, but not 100%, as I was saying. So we've been doing some simulation. Can you engineer a bit the nanofiber and try to find a way to increase this coupling? And we found out that if you kind of are able to grow structures on your nanofiber, we've built this 4 walls structure. You can push up to 70% with quite a simple structure to realize the coupling efficiency in your system, with like depending on which material you want to use. So you can push from like this 25–30% to hopefully 70% coupling. And so we've been doing that in the lab. We found a way to actually grow nanostructures on top of nanofibers. This is really not an easy process because your fiber is vibrating when you try to use, so you're using electron beam induced deposition. So you have to be a bit clever and defocus actually your beam. So you're less precise, but the nanofiber vibrate less and you can grow structures wherever you want in a deterministic fashion. And you can use many different materials. Here it was done first with platinum material, but you can grow also now we are growing dielectric structures, graphite at the moment, but if you have a precursor such as SiN, you can do it as well. And so we can also grow, my mouse, you see it? Yeah. You can see here we have a little nanorod and we can grow structure around, so we can find it in the SEM and then grow things around deterministically. So this was a beautiful technique done by Antonio and Mariana that they made in the lab, made possible in the lab. So at the moment we are developing this nano diamond nanostructure interface, where we are like doing this kind of wall shape in our system, and also having fun writing the name of our lab on top of a nanofiber. So this is like the two guys that managed to do that. And so the idea is to try to see now if we can get more single photon than only using a nanofiber. And so it's in progress. We managed to make one where we have nano diamonds and the wall. So we'll see if it works. Another thing we're doing is like do a bit of different thinking. Is instead of you're always a bit limited by a nanofiber because the refractive index is a bit low, so the field can be evanescent, it can escape. So even if you have an emitter inside of the nanofiber, you won't get more than 50% coupling in your system. So what you can do is get a waveguide with a higher refractive index material. For example, diamond, very high refractive index, and you can have color centers in it, such as silicon vacancy centers. So with this, you already start with a coupling efficiency from your color center to the waveguide mode to between 60%, 95%, depending on how good, what is the direction of the dipole. We can go in detail about that. But then the problem of diamond is that then the light stays inside of the diamond. It's very hard to outcouple. So that was Altea's project. I hope you saw her poster at lunch. What she's doing actually is using the nanofiber as a way to outcouple from the diamond. So we have our tapered nanofiber, and we basically taper also our diamond waveguide, sorry. And then if you adiabatically taper the diamond, you can outcouple. You see that most of the light is here. And if you go across this system, you get more and more light from the diamond waveguide to the nanofiber with theoretically much higher than 90% efficiency. So Altea developed a pick-and-place technique where in 5 minutes she can just grab a nano waveguide and put it on a nanofiber. I didn't want to say more because she had a poster, so I hope you discussed with her on how to do that. Okay, so this is like our what we do in our new team, but also we can wonder about why do we want to increase light matter interaction. So I told you about photon collection efficiency. It's really it's great using waveguides, but not only, and we've heard of it today as well in the other talks, the fact that if you increase the probability for an atom to emit a photon in a waveguide, you increase the probability for the photon, if you reverse it, to see the atom actually and to interact with the atom. And you can use it actually as a way to do photon-photon interaction because Star Wars is wrong. You don't have interaction in vacuum or in air. You need actually matter to have interaction between light, between photons. And obviously, atoms are like the smallest part of matter. So you can enter this field of giant nonlinearities where you have an extremely large nonlinear response at the single photon level even of your system. So you can find it in many other systems using E18 atoms, Rydberg atoms. We've heard about it today as well. And more generally, we are wondering what happens when. So we've heard of what happens when any quantum state interact with a two-level emitter in a waveguide. Actually, so here it will be results done in my postdoc. So using self-assembled quantum dots in a photonic crystal waveguide. So just disclaimer, but it can work for any system. Basically, for example, if you send a single photon onto a two-level emitter in a waveguide, what happens on resonance? You get a reflection. You get a single photon gets reflected. So if you come with your laser, you scan across the resonance of your atom, and if your atom is well coupled to your waveguide, you will get actually a reflection. So if you check in transmission, you will get a drop of transmission. And then, so this is what we could see in the lab, a pretty big drop of the transmission of a laser, attenuated laser in a waveguide. But then when you start to have two photons interacting with a two-level emitter in a waveguide, you get a completely different system, and that's where you get this photon-photon interaction. They don't they interact together, they do something to each other. And if you come basically with a laser, just a Gaussian 2-photon wave packet, so this is, we try to make it as Gaussian as possible, in the waveguide, first you get a transmitted wave function at the output, so unlike single photon, 2-photon can get transmitted. And you get a completely different shape with basically some bunching at the center. So the time correlation, the time of arrival of your photons, you can see them bunched, so like if they were attracting each other, if you want. And basically there is a whole bunch of phenomena there that, well, it's a very active field in the literature. You can have photon-photon interaction, you can have creation of bond states. You actually create time frequency entanglement with this system and even squeezing. So completely different behavior when you have 1 photon and 2 photons. And so what we have been doing and the reason why we are pushing our experiments further and further is to try to do quantum state engineering actually using a single atom, a color center in diamond, but it could be used for anything with any other 2-level emitter in a waveguide. And so we've been recently doing a simulation, it's a paper by Sebastian also that inspired us on if you send Gaussian pulses, so you send what we call a classical state, a coherent state. What kind of quantum state do you get at the output? And so what makes everyone excited is that you get this Wigner negative state, which means highly quantum state. So unlike cavity QED, the system is multi-mode in a waveguide. So you don't have a single spectral temporal mode, you get many different modes. So it's a bit more messy. I'm not saying that it will be the most efficient way to do quantum state, but the physics there is very interesting on which type of mode do you get, which one gets populated, what do you get entanglement between those modes. And we've also been playing on what if you, instead of sending a coherent state, so just a laser, you send what we call the squeeze state. It seems like we are creating some kind of interesting shapes that seems to look like a Schrödinger kitten for people who are familiar, a small Schrödinger kitten, for people who are familiar with the shape of Wigner function. So might be an interesting way to generate some optical quantum states other than just a single photon. On this, I hope I'm on time. I'm finishing. So I will say a huge shout out to the team that we have at LKB in Paris. So including Antonio, Lucien, Altea, and Thomas that are the heroes in the lab trying to do all these complicated experiments. With that, I can take questions if we still have time. I hope it was not too long. It was good? I was fast. I was even faster.
Yes, I think there's
I thought it would be
plenty
too
of time
long,
for
but
questions.
okay, that's good.
Thank you for interesting talk. So I have a, sorry for dumb question, but I have a question about the wall structure. So why, please, could you explain why such structure improve the coupling efficiency? Because intuitively, that might scatter the evanescent field. So yeah, please.
Yes. So if you're using metallic, it scatters a lot, actually. But so we got inspired first by typical photonic crystal waveguide. The same way you would drill in a nanofiber something repetitive, it doesn't scatter much, right? But it's imperfect, what we do. And that's why we only have 4. Actually, if you start to increase more walls, all of them scatters a little bit. So it's a trade-off between what gets scattered. If you put too many, it just scatters more and doesn't couple more the light in the fiber. But if you have a few, it still have a bit of a photonic crystal effect, and that way. But they scatter a little bit, even if you use the electric system. That's why we only have 70%. We don't have a theoretical 100%, I think. And the shape, well, we were growing pillars, and at some point we increased the dimension in one side because it was easier to make a square in our simulation. And so Lucien just increased one dimension, and we're like, oh, it's more. So just trying.
Yeah, thank you very much.
You're welcome.
Any other questions? Maybe I have a question then. So you showed this kind of plots at the end where you you said if you send squeeze light on a single emitter, you can generate kind of what looks like Schrodinger kittens.
Yeah,
Do you know if there's a limit to that? So in other words, like, I mean, is there really a way to generate like kind of large Schrodinger cats, or it's really just kind of like a finite size effects?
It seems to be small. So we only have 1 2-level emitter, so I wouldn't expect anything too big because your system saturates. If you keep on increasing the squeezing, you lose the negativity. So yeah, it seems to be just funny, but at least we are going beyond the 0+1, which is cool already, since we have something happening to the 2 photon. Yeah, I think if you want to make a real cat or JKP, you need more emitters in the system, as you might know.
Okay. Okay, well, so if there's no more questions, let's thank Hanna again.